Um, we're going to take this pretty casually. I'm very happy to take questions whenever you'd like. Um, I should say at the start that I'm mostly an academic and not an industry data scientist. So some of the questions that I tend to think about, some of the tools that I tend to try to develop, are more focused on some types of problems than others. And I'm going to do my best today to focus on places where those problems overlap with industry problems, but you'll have to let me know how I do as we go. So the subject of this talk is about causal inference and NLP, especially as it's applied to electronic health records. So I'll go into the pieces of those one by one. And we start with the observation that there are these two kinds of different schools of working with data. There is the one that we're all most familiar with, which is the data science and machine learning worlds. And that's the stuff that gets most of the attention. It's the stuff that gets most of the startup money. It's the thing that most companies are more interested in. And then there's this kind of other world of working with data called statistics. And statistics and data science are obviously closely related. They share a common ancestor, but they have very different philosophies about how things work. My old professor used to say that data science is just cowboy statistics. And what he meant by that is that these two sets of schools have a lot of differences. One of them is in the goals. So if we're doing data science, if we're doing machine learning, the thing that we most often care about is prediction. Whereas if we're studying statistics, most of statistics is focused on estimation, commonly something that we're going to call a treatment effect. We care about things like policy evaluation. We care about things like average treatment effects. You might hear terms like that. And we'll get into how these two things are different in a little bit. Another difference is that they have differences in the types of approaches that they prefer. So in a data science and ML world, we can have super complex methods. They can be as complex, as technical, as advanced as we would like. As long as those things produce better predictions or continue to be scalable, more complexity is never going to be hurtful. On the other hand, in statistics, we have this very strong preference for simpler methods. These are things that are easy to understand and easy to explain. These are things that tend to be computationally simple, things that tend to be provable. And whereas prediction and treatment effects sometimes go hand in hand, these two are very clearly opposites. We also have differences in what kinds of goals what types of proof that we use. So in data science and ML, we think about things like accuracy in terms of things like AUC, ROC, F1 scores, things that we're all familiar with. In statistics, we tend to care about something called precision, and something called calibration. And these are often very different goals. I'll get into, again, how these are different a little later on. Finally, the big difference here is in something called interpretability. This is related to the complexity simplicity model, but in data science, we don't necessarily care, what neuron 6,347 is doing in a neural net. We don't necessarily care what, parameter 3,000,000,005 means or what value it holds. Whereas in statistics, that's pretty much all we care about. We'd like to get numbers out that have interpretable, concrete meanings, things that we can use to make decisions. But insofar as statistics has this preference for simplicity, for interpretability, for estimating precision, this has very serious drawbacks when it comes to using advanced forms of data, things like text data, things like image data. Statistics isn't very well suited to handling these types of things, whereas data science and ML are essentially custom built to handle these types of data. So the goal of this talk is going to be, how can we get these two schools of thought to work together? How can we produce tools at the intersection of statistics and data science, or ML, that let us use text data, that let us do prediction or treatment effect estimation, where we can take accuracy or precision, and ideally where we also get interpretability and preserving as much simplicity as possible. So we'd like to try to get all the benefits of both of these things and meet all of their requirements separately. So this is going to be the philosophical overview of a lot of my work. It's how can we combine these two schools of thought and make everybody better off? And the application that we're going to go over today is about healthcare, but I'm going to do my best as we go to try to open the floor and explain some other cases where we might have these types of problems and we can benefit. So I'm going to claim that there are three ways that we can use text data. We can use data science tools for handling text data to help us with statistics. One of them is going to be imputation. Another is going to be matching, and the third is going to be heterogeneous treatment effects. I'm going to spend a lot of time going through these things one by one, but the most simple is imputation. Imputation is the name for a general class of tools that we use when we have missing data. If we have missing data in our data sets, which, as you all know, we always do, there's never a data set without missing data. If somebody tells you their data set doesn't have any missing data, they're lying. So when we have missing data, what types of tools can we use to address it? And how can we use text data and data science tools to get good statistical improvements in our imputations? So I'm going to show that we can use text data to help us fill in missing variables. And we're going to do that by including the text data in some standard missing data imputation procedures to get a better job at filling in our missing data. Now, if the only thing you take away from this talk is that you can use text data to help you fill in your missing data, I'm going to consider that a win, because everyone has missing data. And a lot of the time, that missing data is accompanied by text. And so we can use these two things to our advantage to improve our results basically for free. Now, a little bit more on the academic side, we're going to think about matching as well. Now, matching is a set of tools that statisticians are really, really fond of to help us take an observational data set and extract out a portion of the data that looks a little bit like a randomized experiment. We'll get into why we want to do that in a little bit. But matching is only as good as the data we have to match with. That is, if we only have 2 or 3 variables and those variables have a lot of missingness, our matching isn't going to be very good for reasons we'll see soon. But it turns out that just as we could with imputation, we can use text data to improve the quality of our matching and do a better job at extracting a randomized experiment from observational data for free. And finally, when we're doing treatment effect estimation, we might also call this A/B testing, program evaluation, anything like that. When we're doing these types of A/B tests, often we care about what statisticians are going to call heterogeneous treatment effects. What this means is if we run, for example, a marketing experiment, we might want to know whether the A/B test that we conducted produces more of a benefit for men than it does for women, or whether it produces, more of an effect for old people than it does for young people. These are heterogeneous treatment effects. Perhaps we might calculate, that our new ad campaign produces a 3% increase in ad views, but maybe that 3%, maybe 80% of that 3% comes from men and only 20% comes from women. Those are important pieces of information that we'd like to know. And I'm going to show that we can use text data to help us estimate these better as well. In particular, we're going to ask the question, which subgroups of the population should get some treatment, which sets of our user base get a new message, or in this case, which medical patients are the best fit for some kind of medical procedure. And when we use text data, it gives us new ways to slice our population into subgroups, which lets us do a better job at figuring out who to target. And if we have a better job knowing who to target, we can target more intelligently and get better outcomes for our A/B tests. So that's going to be the three things that we're going to go over today. And we can focus more on one or the other depending on what people are interested in. And as I said, feel free to interrupt me or raise your hand if you have any questions or if any of these things really speak to you. And an important thing that I want to note is that we can do all three of these things together. So within one data set, we can use the text data to do imputation, to extract a randomized study, and to figure out heterogeneous treatment effects. So we can improve three parts of our data analysis pipeline, all for free, just with a little bit of NLP. And you should know that all the data that I use for this study and all of the code that I've written to do it is going to be freely available online. And we're even working on a software package in R to implement all of these things. And we definitely welcome people re-implementing it in Python or whatever you'd like. Okay. So any questions so far? Okay. Well, let's go on from there. So I'm going to start with something that we think a lot about in statistics, which is the idea of causal effects. And we all know that experiments are the gold standard. If you want to know whether an ad campaign works better than some other ad campaign, you do an A/B test. If you want to know if a new vaccine works, you run a randomized trial compared to some kind of placebo or a control.
Sorry, Aaron,
but
here's a question about any equivalent Python package.
No. So unfortunately, most statistics work happens in R. But fortunately, R and Python happen to be pretty mutually intelligible. So I would say most people who are familiar with Python should have not a too difficult time translating R code into Python. Now, one thing that I'm excited to experiment with is supposedly, GPT-4 is pretty good translating from one programming language to another. It might be worth trying just, pasting the entire R library into GPT and seeing if it translates it. If it does, then that would be super cool, but we'll see. Thanks for the question, though. Okay. So experiments are the gold standard. If we want to know how much something works compared to an alternative, we have to do experiments. But unfortunately, most of the data that exists in the world is not randomized. And this especially applies to a really, really valuable source of data called an electronic health record. Now, electronic health records come from hospitals, typically. Some of you might be familiar with it. If you are familiar with the electronic health records already, I apologize. But the idea behind these data sets is that a patient comes into the hospital and the nurse takes their height, records their temperature, records their blood pressure. The doctor maybe takes some blood and does some tests to figure out their cholesterol, things like that. And the doctor will write some notes down about their evaluations of the patient. And in particular, electronic health records are valuable because they have tons and tons of data. There are lots of covariates that are collected. Every patient, every treatment that patient receives, when those treatments were received, and it's collected at scale. So these data sets grow very rapidly, and they tend to be very big to begin with. And another reason that we like using these is because they're about important stuff. With these data sets, we can learn really valuable things about how to improve healthcare, how to save lives. And sometimes we learn that some of the things that we were doing that were really expensive are actually much more expensive than they're worth or actually costing lives. And that's super valuable stuff to know. So what we'd like to be able to do is to use these electronic health records, even though they're not randomized, to figure out how effective various medical procedures are. That's the name of the game. How can we use this extremely rich, very valuable data to get data sets that are as if we did an A/B test? Of course, we all know that there are some problems here. There's data quality problems. That is, these electronic health records sometimes have missing data. Sometimes there are things that are measured wrong. For example, the patient steps on the scale and weighs, 84 kilos, but the nurse accidentally enters that as 48 kilos. That's a big difference. And this kind of thing happens all the time. As well, we know that doctors and nurses are really busy people. And so sometimes they just forget to put in some of this information. Another problem here is that there's bias in this data set. There's selection bias, there's omitted variable bias, and lots of other types of biases we're probably familiar with. And then third, there's just an overwhelming amount of data. We're talking, hundreds of gigabytes of really dense data. And so it's hard to even know where to start. So I'm going to ask a question here, and I'm going to see who can get the, what about data privacy? Yes, data privacy is a huge issue here. These data sets are not typically publicly accessible. There are lots and lots of startups that are founded on access to these data sets. Hospitals, universities will often spin off companies to do analytics based on these data sets. Researchers typically have protected access under, data use agreements, but it has to be anonymized. It's too valuable, too sensitive otherwise. Yeah, good questions. Okay, so here's a research question. Hopefully you guys can help me with this. Does transthoracic echocardiography save or kill patients? Now, it starts with this paradox here. Why do patients who get stronger treatments tend to die more? This is the question that I pose to you, the audience. Does anyone have any idea why patients who get stronger treatments tend to die more? Feel free to think about it for a moment. Yeah, exactly. So the reason that patients with stronger treatments tend to die more is patients only get stronger treatment if they're already pretty sick. So if we just look at observational data, if we look at these large electronic health records, we see that there's a negative correlation between getting really strong treatments and how many days you survive. So this is just an observed correlation. So if we're just looking at this correlational data, we might assume that all doctors are doing is just killing patients left and right with these really expensive medical procedures, costing a lot of money, costing a lot of lives, not getting anything done. We call this selection bias. That is, it's not random who gets the treatment. The only people who tend to get these strong treatments are people who tend to die more anyway. So if we'd like to figure out how effective these stronger treatments are, well, we have two options. One option is that we can use a randomized trial where some patients get strong treatments and some patients get a placebo, and we randomly decide who gets which. What that gives us is it means that the patients who are sicker are not disproportionately going to get the stronger treatments. But these randomized trials are expensive, and we already have this data. So how can we figure out how to get rid of this selection bias just with the data we have? That is, if we control for selection bias, which patients will benefit from the treatment, and by how much will they benefit? So the data that we're going to be using here is a data set called Mimic4, Mimic3. We use the newest version. And this is a data set from the large hospital system in Boston in the US. So this data set has lots of different patient-level covariates. We have their charting data. So that's things like their fluids, the medications they're taking. We have vital signs like their heart rate and their blood pressure. We have laboratory tests, including things like blood work and microbiome. We have X-rays, we have CAT scans, we have information about the patient, we have information from billing. The insurance data tends to be the best data, of course, and so we know exactly what they were billed for. And then if they die, we know what the government thinks they died of. That's from the Social Security Death Index. Then we de-identify everything to preserve privacy, and that's the database that we're using. This is a super valuable data set. It has tens of thousands of citations and publications coming out of it. And in particular, we're going to look at a data set by a professor named Monin Feng, who uses this data set to explore transthoracic echocardiography. So transthoracic echocardiography is this procedure that we see right here. So we have a patient who is lying in a hospital bed, and the doctor has this little wand here that she's passing over the patient's rib cage. And then on the screen over here, we see the heart. So transthoracic echocardiography is typically used for viewing the heart. It's typically used when we have patients with heart concerns. And it's very nice because while it's somewhat expensive, it's not invasive. So there's no reason why transthoracic echocardiography should do damage to you. It's not like a botched surgery. It's not like some kind of medication with side effects. It's just passing a little wand up and down your chest. Yet, for some reason, if we look at the correlations between how long you survive and whether you received transthoracic echocardiography, we see a strong negative correlation. Okay, so what do existing researchers do to try to extract out a randomized trial, an A/B test from this medical data? Well, they do a procedure called matching, where we find patients who look very similar on all of their covariates, patients with similar demographics, similar age, similar birthdays, similar neighborhoods that they live in, similar medical histories. But one of these patients happened to receive transthoracic echocardiography, or TTE, and the other patient did not. So we look at two pretty similar patients that have different treatments, and then we try to compare them. So instead of only looking at really sick patients who did get TTE and the healthy patients who did not, we try to find patients who look equally sick, but they have different values for the treatment. In this case, the treatment that we're looking at is TTE, and the outcome here is 28-day mortality. So that is, did you survive for the next 4 weeks after you were discharged from the hospital? Okay, questions so far? I know it takes a minute to type the questions into chat, so I want to make sure we take time. Okay, we'll keep going. So we're going to start with missing data here. This mimic data set, it's pretty good. I like it a lot, but it has a lot of missing data, unfortunately. Every data set does. And in fact, missing data is going to be a big problem when we're trying to estimate whether TTE helps or hurts and how much. That is, we say missing data is a causal inference problem. In a lot of situations, and I've seen even very talented professional data scientists do this all the time, the most common solution to missing data is just to pretend that it doesn't exist. We have, a billion rows of data, and maybe a million of them have some amount of missingness. So we remove the million of them that are missing. In statistics, this is like a cardinal sin. This is there's a famous paper titled "Listwise Deletion is Evil" because of how harmful it is to the kinds of analyses we want to do later. So in our data set, we have 46 variables. Of them, 15 have some missing values. The average amount of missingness is 11%. The median amount of missingness is 4%. That is, on average, among these 15 variables, 11% of the entries are missing. This is not good. That's way too much missingness for us. So what we're going to try to do is we're going to try to use our text data to fill in the missing data in this mimic data set. And that's going to be our first task. If we can fill in the missing data in this data set well, that's already by itself a super valuable piece of contribution to this data. If you as a professional data scientist get hired for a company to help with their data backend, and their data set has this much missingness, and you help them fill in all this missingness, you're adding untold value to their data set, which is a core piece of their product. So what we're going to do is we're going to use some pretty straightforward NLP tools to create a text projection for each variable. And then we're going to take the missing data plus the text projections, plug them into a standard missing data technique called MICE, multiple imputation with chained equations. And we can use cross-validation to estimate our RMSE, our root mean squared error, and our R squared to figure out how well we're doing at imputing missing data. So in other words, we add in some fake missing data, and we try to impute it using normal statistical imputation techniques. And we see how well we do with RMSE. Then we try a second approach where we add on an NLP step to our standard statistical missing data test technique. And then we try again. We try to see how much better we do at improving our imputation via RMSE. I'm happy to spend more time on the details of this method, but I don't want to get too technical. I want to keep it at a fairly high level for now. And so here's what our results look like. Here we have the variables with missingness. We have lactate, which is a blood test. We have PO2, PCO2, pH. We have weight, platelet and hemoglobin count. Again, we have more blood tests. We have their temperature. And over here on this y-axis, we have how much of that variable is missing. So we see that lactate is the most missing at 40%. Temperature, we have less than 5% missing. And if we just try to fill in that data using our normal statistical techniques, this is where our RMSE is. So we see that the RMSE for lactate is 0.75. That's okay. For PO2, it's almost at 1. For WBC, it's almost 1.2. So these are pretty high levels of RMSE. These are the blue dots here, our standard technique. Now, the red dots here are our RMSE when we use an NLP step. We add in a fairly simple NLP step into our missing data procedure. And we can see that across all of our covariates, we get a strong reduction in error. We're doing a much, much better job at filling in our missing data when we include text. We include this NLP step in trying to in trying to do so. So most of the time, we have this missing data sitting here. We use these standard methods. We get the results here in blue. But pretty much all of the time, and especially with these electronic health records, we have this text data just sitting there. And we haven't figured out how to use it yet. But we can use insights from data science and NLP to use this data that we already have just sitting there to solve our old problems better than we could have before. So that's the first result. Yeah, please go ahead.
Yeah, quick question there. This missing data assumes or kind of implies that there's potentially a problem with data quality, and so we are kind of this method treating the filled data as source of truth. But if there's some missing data, then potentially there might be issues with wrong data as well. So there should be this assumption that the existing filled data should be correct. But how can we be sure about that?
Yeah. So if we have some missing data, does that also imply that some of the data that isn't missing is wrong? It doesn't necessarily imply it, but I think you're right to say that typically in the real world, those two things correlate. They tend to go together. Our contribution, I would say, isn't necessarily that we're going to fix all the missing data or data quality problems you have, but we're going to show that you can use relatively simple tools to do better, even if we can't get all the way there. So we're never, of course, going to be able to get all the way there, but we can definitely do substantially better. Now, what if, for example, some of the data that we're cross-validating with happens to be wrong? Well, on average, unless it's wrong more than it's right, then these results are still going to hold. They might be slight underestimates, or they actually might be slight overestimates of how much improvement this method produces. But of course, we always have to be considerate of the various sources of possible error in our data.
Makes sense. Thanks.
So here's the average reduction in RMSE is 12.6%, which I think is pretty fantastic. Any statistical method that can reduce your RMSE by 12.6% can improve your data quality. That's improving your data quality by 12.6%. And especially in cases where your data set is, millions or even tens of millions of dollars of value, you can math pretty simply. So the next problem we're going to approach is the idea of matching. Matching, as I mentioned, is that it's a common tool for trying to get causal inference when we don't have a randomized experiment. And the way it works is we find groups of patients who are equally likely to receive some kind of treatment, or we have groups of users or customers who are equally likely to receive some kind of message. But importantly, different ones of these users or patients actually get different treatments. And in statistics, we say that this is kind of like extracting a randomized study from within an observational data set. We're removing all the people that never get treatment. We're removing all the people who would always get treatment. And all we're left with are people who might or might not get treatments, reducing selection bias. In statistics, we say that after we do this, the treated and the untreated groups should be balanced. Balanced just means they should be similar on all the covariates we observe. So to talk about this in our medical trial context, we have a lot of patients who receive TTE, and we have some patients who don't. And the patients who receive TTE tend to be much sicker than the patients who don't. So we're going to look at the covariates the demographics, the lab tests, the medical histories of all of these patients. And we're going to throw away the patients who are so sick that they will that everyone who looks like them will get TTE. Similarly, we're going to throw away all the patients who are so healthy that no one who gets TTE looks like them. And the only patients that we're going to be left with are patients where there are some of them who get TTE and some of them who don't, but they generally look kind of similar. Now, the big problem with doing this kind of causal matching is that it's very sensitive to how much information is in your variables. So if I only know the age and the weight of my patients, there are going to be patients of all ages and all weights who get TTE and who don't. So I can't really use age and weight by themselves to figure out which patients are sicker. If I think that really it's how sick you are that determines whether you get TTE or not, then I need to come up with a really good proxy, a really good set of variables that capture how sick you are. And if I can't do that, then it's possible that there are still some confounding variables that are getting in the way. So this is what a matching balance looks like. On the x-axis here, we have the standardized difference in means. That is, how much bigger is the control, or how different are the values between the TTE patients and the non-TTE patients? So this variable over here, this is a variable where the TTE patients had a much higher value of it than the non-TTE patients. This variable over here says the non-TTE patients had a much higher value than the TTE patients. And these in the middle say that the TTE patients and the non-TTE patients had pretty similar values of these variables on average. And this is what you don't want to see when we're doing a matching study, because this means that there are all these confounders. All of these variables here are selection bias, things that might lead to some patients getting TTE and some patients not. So instead, what we can do is we can use these matching methods to kind of selectively throw away observations. And we continue to throw away observations until we get something that looks like this, where pretty much all of the variables that we have that could be leading to selection bias in who gets TTE all look the same. That is, now our groups of patients who get TTE and our group of patients who don't get TTE, they're the same on average. The 46 variables that we have. 46 is, it's not a million variables, but it's a lot of variables. It includes lots of really valuable information about who these patients are and how sick they are.
These are all the genius variables. We're not looking at like attributes of the patients or some other things.
These are continuous, categorical, binary. These are all sorts of different variables. But there's one problem here with these variables, and that is that we're only looking at 46 of them. These are the only 46 we have that we think. But it turns out that a lot of other variables that we might also need to control for. So over here, we have the 46 variables that are collected routinely as part of the MIMIC data set, things like weight, height, blood pressure. And we can see that after we do matching, we get pretty good balance. But these second set of variables, these are variables that we find in the text data. So here we're mining the notes that doctors and nurses write about, and we're collecting common words or phrases from these notes. And when we do this, we see that even after we we remove patients with extreme values and get our balancing, it's still the case that our TTE and non-TTE patients have very different content in their doctor and nurses notes. So the doctors and nurses write about these people differently. it means that there's still selection bias in our data set. So if we're just looking at the non-NLP based data, it would look like we've selection bias. But when we consider the text NLP data as well, we see that there's still selection bias we hadn't accounted for. And so what we're going to want to do instead is find a way to to include this text data in our matching methods. And that's the results in red here. We see by including text data with some very straightforward NLP methods into our data set or into our matching methods, we can remove a lot more selection bias than we could have before. And these methods are really straightforward. They involve taking our doctors' and nurses' notes and embedding them using word embeddings. Could be any word embedding, but in this case, we use a word embedding specifically trained on medical text. And we include those word embeddings, the raw word embedding vectors, in our pretty standard matching procedures. And we see that we get a very strong improvement in balance. So our balance goes, or our imbalance goes from 0.14 to 0.11 to 0.09, which is, like almost a 20% reduction, improvement in balance. And on our structured variables, it goes from 11% to 3% and doesn't actually get much worse. So oftentimes, if we want to balance on more variables, we need to sacrifice balance on different variables. But we see that we're not actually sacrificing anything here. Okay. So here's the last location I want to show. And this is my favorite. So this is about heterogeneous treatment effects. And the question is, which subpopulations are going to benefit the most from our treatment? Which groups of users are going to benefit the most from our ad campaign? I'm a political scientist, so we care a lot about elections. Which types of voters are going to be most responsive to a TV ad or a newspaper mailer? Or if you're an economist, you might care about development. So which types of businesses are going to improve the most with loans? So these are really big, important questions. And what we're going to do is we're going to start with the data set that we've built. We've used our text data to fill in our missing data. Then we've used the text data again to extract a randomized experiment from that data set. And then we're going to try to figure out for each of our covariates, which, what values of them determine heterogeneous treatment effects. So for example, perhaps we think that patients who are heavier, tend to be overweight, are going to benefit more from TTE. This is a pretty reasonable assumption. So we'll use some automatic clustering methods to figure out which value of the weight we should cut off, or we should use as our cut point. And maybe it's, 100 kilos. So maybe anyone above 100 kilos is going to have a very, very strong effect from TTE. And if you're below 100 kilos, the effect is going to be not so good or not so strong. If this is what we find, that's great. It tells us that we can save our money. If someone's under 100 kilos, we don't have to give the PTE. And if someone's above 100 kilos, we get more benefit for doing TTE on them. So, and we're going to do this for every single one of our 46 structured variables. Now, for our text variables, we're going to do something a little different. We're going to use a very simple bag of words. We're going to look at all of the unigrams and bigrams, the words and phrases in our doctor and nurse's notes, and we're just going to see whether they're present or absent. So if the doctor's note mentions, for example, obese or heart disease or pale, then we're going to code that as a 1. And if the doctor's note doesn't mention that, we're going to code it as a 0. And then for both subgroups, we're going to identify how effective TTE is. So what is the average mortality among people who get TTE in the 100 kilos group? What is the average mortality among people who do not get TTE in the 100 kilos group? What's the average mortality among people who get TTE in the under 100 kilos group, and et cetera, et cetera. And in a statistical way to do this, that is, we're conducting a linear regression where the outcome is mortality. We have an intercept. We have whether they received TTE or not. And we have an interaction term with the subgroup. The subgroup here is whether they're over 100 kilos or not. This subgroup is whether the doctor's note mentions obese or not. And just to reiterate, it's not just obese, not, it's, every single possible word. It's not just overweight or not, it's every single possible covariate. Yes, please.
No, yeah, just on that last question, point on text variable. So is it like something hand coded, like the rules, like the word is present or not, or is it just like inferring from the whole, the back of words of whole text documents present?
Yeah, you can figure this out automatically using the bag of words. Exactly. So you don't have to do any hand coding here. There's no, in none of this work do you have to do any hand coding. One of the things that's very nice about this is with no additional hand coding and just a little bit of software, you can implement all of these tools for free. So what do we find after we doing this analysis? Well, we find that generally patients where the doctors note that they have a severe heart condition tend to benefit the most. This is pretty straightforward. If you have a pretty severe heart condition, then an analysis that looks at your heart, that should be pretty good, pretty helpful. But we also find that patients with notes indicating that they have non-heart conditions are actually actively harmed. So if a doctor's or nurse's note mentions something like a blood disease or cancer or some kind of blunt force trauma, if you give these people TTE, it's wasting precious time. They should be getting some other type of treatment, but instead they're getting TTE, and that's harming their chances of survival. And it turns out that that's happening by quite a bit. So here's some results. BNP is a blood enzyme that your heart releases when your heart's in trouble, to oversimplify. This is the overall treatment effect if the value of your BNP is below a certain threshold. If you have a low value of BNP, then the effect of TTE on your survival is very small. It's just about the average, just about 5 percentage points. You're 5 percentage points less likely to die if you get TTE, if you have a low value of this covariate. But if you have a high value of this covariate, then you're about 27 percentage points more likely to survive. That's a big difference. Of course, the standard errors here are very large, but that's okay. So here are 5 structured covariates. The circles indicate the low values of those covariates. The triangles indicate the high values of those covariates. So we see that for lactate, if you have a high value of lactate, then getting TTE means you're about 18 percentage points more likely to live. Whereas if you have a low value of SAPS or SOFA, these are severity of illness, these are how sick you are measures. Actually, it looks like TTE hurts you. So if you have a low value of SAPS, then getting TTE has a negative treatment effect of about 6 percentage points. You're 6 percentage points more likely to die if they give you TTE despite having a low value of SAPS. So that's something that's good to know. But these 5 variables here are text-based variables. So if the doctor's note mentions the phrase BNP, if the doctor's note mentions the phrase intubate or measures or dependent, these indicate that you have very, very strong benefits from TTE. The strongest covariate here is the BNP structured variable. That is, if you have a high value of BNP, you have about a 26 percentage point gain to your survivability from TTE. But here we have 5 variables from the text with all much stronger additional benefits from TTE. So if your doctor's note says measures in it and you get TTE, you are like almost 50 percentage points more likely to survive. That is, if we can figure out ex ante who the people are who are going to benefit most, we can target this treatment more effectively. And using the text, we can find a whole lot of different words in the doctor. One thing that I really like about this is that the text BNP and the structured BNP have almost identical effects. So we consider this a pretty strong evidence that what we're doing makes some sense. So to wrap up a little bit, we have 51 text variables, all with a stronger benefit from TTE than the strongest non-text variable. We can use this text, we can mine the valuable information in it to help us do a much better job of figuring out which patients should get which treatments. You can easily consider extending this to, for example, politics, where we figure out which types of voters are more likely to benefit from certain types of ad campaigns based on the types of things those voters say on Twitter. We can figure out which companies in the developing world will benefit the most from a micro loan based on those companies' corporate records or mission statements. Lots and lots and lots of applications. Yeah, please.
Yeah, sorry, didn't mean to interrupt, but just curious in terms of, you mentioned interpretability at the beginning, and like here, I'm just wondering, the words like Thursday or measures, is it something that maybe happens just because of, doctors tend to write more notes when the patients are really sick and not when they don't think they're sick or something like that?
Yeah, so that's a good question. Do doctors tend to write more when the patients are sick? Not necessarily, actually. This Thursday variable is actually a very well-known phenomenon. There are very strong day-of-the-week effects. My favorite example of this is that if you happen to have a heart attack on the day of the International Heart Doctors Conference, you're much more likely to die. Because all the good heart doctors are at the conference, and so you're left with the bad doctors that didn't get invited to the conference. The same is true of Thursday. Different types of doctors come in on different days of the week, at least in the United States. But to your broader point about, some might just be random, we do some statistical corrections to account for, multiple testing, and we find very strong results. So, a lot of these results, all of these here are robust to, like, these are still statistically significant, even after correcting for multiple testing. So to wrap up a little bit, we almost always have text data that comes with some of our other data sets. And we don't often know how to use it. We often just kind of leave it there, or maybe do some clustering analysis or something like that. But there are lots and lots of ways that we could use it to improve our data analysis in a lot of different stages. that we can get for free. We don't have to do any more hand coding. We don't have to do any fancy machine learning. We can use very simple, straightforward NLP methods. We can use it to get better missing data imputations, to do a better job of balancing our data sets, to do a better job of identifying which subgroups are likely to be helped more, to benefit more from our A/B tests. And all these methods are very easy to implement. Nothing we're doing here is advanced NLP. Nothing here we're doing requires advanced computing or big, computing hardware. We've designed all of these tools to be based on the statistics concept of the simplest stuff that we can do that works. If you have any questions about how to implement these things, or if you have other ideas for what types of contexts you want to use these things in, please feel free to reach out to us by email. I'm very, very happy to chat about these things. These are my beautiful co-authors at various universities throughout the US, MIT, Harvard, Bentley. So thank you very much for your time. I hope this was interesting.